Hi, my name is Griffin Price, and this is Lab 4 Circuits. To introduce this lab, we're going to try and predict the behavior of circuits with resistors in series and parallel by measuring values of current and potential differences with multimeters, and to understand how resistors and capacitors behave in circuitry. Some fundamental principles are the loop rule, node rule, Ohm's law, conservation of energy and charge, and the steady state circuits, and some preview of results. The calculated values that I calculated match the ones from the online model. Specifically, when finding time, both at around 6 seconds, so we'll see that later. The system and surroundings, the system being the circuit, and surroundings being literally everything else. I'm observing the behaviors of capacitors and resistors in different combinations on the online circuit creator. I'm assuming that the natural resistance in the wiring and emitters are negligible, and some possible source of error could be precision of the equipment, and the results could be improved through multiple trials and by using real-life circuits instead of an online one. So for part 1, I have a circuit with two 1.5 volt batteries, two emitters, a 47 ohm resistor, and a 100 ohm resistor. Adding the 147, bringing the total resistance to 147 ohms. Using Ohm's law, I did the total voltage 3 over the total resistance 147 to get current being 0.02 amps. Current is negative if it's observed in the opposite direction. And once an emitter is replaced with a voltmeter, I found that voltage is 3 and that the current is 0, and this is because with an open circuit, current is always 0, right? And the potential difference is always constant. So to continue from part 1, I finished out this little graph given, and B minus A would be a potential difference of 3 volts, C minus B being 0, D minus C equals negative 0.96, E minus D being 0, F minus E being negative 2.04, and G minus F, H minus G, and A minus H all being 0. Overall change in voltage is 0, current is 0.02 amps, and the round trip potential is 0. So when I put the emitter in parallel with a 100 ohm resistor, current went from 0.02 to 0.06 amps. This is kind of because not as much current is contacting with the 100 ohm resistor, and that lack of resistance increases the amount of current due to Ohm's law. Now that I found that the resistance of the 47 ohm resistor, 0.96 volts over 0.02 amps equals 48 ohms, that's close. For the 100 ohm resistor, 2.04 divided by 0.02, giving you 102 ohms, also close. Resistance of wire had 0 volts, so that's automatically 0 ohms. Same thing with the emitter, 0 volts, 0 ohms. For part 2, I used this circuit. I had a 9 volt battery, a 10 ohm bulb, a 20 ohm bulb, and a 200 millifarad capacitor. So with the 10 ohm bulb, I connected it as seen to the left here. The bulb started off very bright and then it dimmed as the capacitor got charged and charged until it's fully charged. At that point, the current decreased all the way to 0. Then I disconnected the battery and the capacitor actually charged the bulb, and it started off very bright and then it got dimmer and dimmer and dimmer until current decreased all the way to 0 once again. For the 10 ohm bulb, it took around 10 seconds to completely discharge. For the 20 ohm bulb, it took, twice as much as that time, 20 seconds for the bulb to completely discharge. And this is using the stopwatch given with the online program. For the time-dependent model, I used the equations given and the data that I found using the online program for part 2. And I graphed it on the slope, or I graphed it using Excel, and I got the equation being y equals negative 0.1646x minus 0.004. That slope is actually our RC value, and using that slope, negative 0.1646, we can actually use the equation given of negative 1 over RC equaling the time. So negative 1 divided by that number is 6.08 seconds. So, all right. Pretty similar to our calculated RC, which would be just resistance times capacitance. Resistance being 30 ohms and capacitance being 0.2 farad, which equals 6 seconds, which is pretty dang close to that 6.08. And this is all using a circuit with a 9 volt battery, 30 ohm bulb, and a 0.2 farad capacitor. Now the what if questions: what if you're doing this lab in real life and used the actual emitter instead of an ideally simulated emitter? What's different about a real one, and how would it have affected the circuits if you hooked it up to? Well, there would be some resistance from the emitter because I neglected it using the online program. And overall, that resistance from the ammeter that I neglected, if I used it in real life, it would definitely lower the current. And what if I was doing this lab in real life and used a real battery to charge the real capacitor with no resistor in the circuit? How quickly would the ideal model predict the capacitor to reach full charge? So ideally, with no resistors, the capacitor was almost charged instantly. In a real circuit, the capacitor would definitely be charged at a slower rate due to the natural resistance of the wire in real life.